was just trying to avoid it, but then I will do that if that is what you guys want. Fair enough.
Yes.
All right.
Yeah.
Let me open the lecture. Okay. Let me share. Mm, mm. All right. So can you all see the screen now? This is
Yes,
geometric
sir. Yeah.
optics. So that is what you see. All right. Good. So this is where we left last time. Um, we haven't really done much on the ray theory. So let's look at that, right? So geometric optics or ray theory, it's all the same. There's no difference between this. All right. Um, so there are few assumptions that we make, because when the theory was formulated, right, there was no assumptions, so to say, because it was perceived that this is the way light is. All right. So there was no need for a certain assumptions, right? It was perceived this is how it is and so on. But then having investigated light beyond its ray nature, now we consider those as assumptions, right? uh, so in ray optics, we use the term ray, right? The primary reason for that is coming from the geometry, right? So you have a starting point, right? And then you have a continuously moving, point, right? So that's what we define a ray as. So the origin is where the light source is, right? And then wherever it moves, that's let me try to get a writing pad. Hmm. Okay. Okay, so you can see the writing pad now, I presume.
Yes, sir.
All right. So the way that the what we call the postulates of ray theory, right? So there we started with, the whole definition of ray is all about having an origin. Okay. So you have light rays coming out, right? So this is a continuous propagating direction, right? So light moves on, right? And this is, in geometric sense, this is nothing but the definition of a ray. All right. So it should always have an origin, right? So it cannot be a continuous line. So this is what we call a ray, right? And it is always represented as a straight line, right? So that um, there is nothing much we can do about it, because that is how people thought light is going to be, right? So all the theories that preceded ray theory could be, approximated down to ray theory, right? So even the electromagnetic wave, right? You can approximate it to ray to explain a lot of phenomena, right? Including reflection and refraction. Though EM theory is much more comprehensive, right, compared to ray, but you can drive a certain assumptions or certain approximations that you can simplify it into a simple ray model. But the ray, as you can see, it's just this you know path. If you have a light source here, you can define, okay, so you have light passing through this, and then if I put a block here, it will reflect, let's say. Okay, so it comes here and it will reflect, and this is what is going to happen, right? But then here you don't talk about what is the effect of these two, all right? So there are two rays here, right? But then in ray theory, you don't really talk about the effect of one ray on the other, right? It's all rather easy to write. So you have ray in, right, would be a summation of ray out. In other words, you have power in equals power out, right? So power in is nothing but summation of intensities in each of this line that I drew here. So this is perhaps a very simplistic way of looking at it, right? But then later on we will see this is not really the right way to look at reflection or light in general. The reason for that is the two rays here, they are not completely isolated. The light, instead of saying it ray, the light, right, at r let's say this is r1 and r2, let's say, right, they are not completely isolated. There is some relation between these two, right? So r1 is there is a relation between these two, right? We'll see what that relation is, and this relation affects when you do the summation. All right, so we'll see that what this relation is and why this is affected going forward. But these are all some of the limitations of assuming that this is a simple ray. All right, so that is the reason why phenomena such as interference, diffraction cannot be explained with ray, right? For some of you might be already done courses in optics and photonics. You will know that interference and diffraction needs not just intensity and the direction of light. There is something called phase, right? Phase is an important property of light that will dictate these phenomena. All right, so that is the reason why we can't explain interference and diffraction by using ray. And another limitation of this is ray model um, is very good if the structure that you are looking at is much larger than the wavelength of light, right? For example, mirrors, a lens system, all these things are much larger than wavelength of light. So ray optics still holds. And for you will be surprised that even the most advanced optical tools, right, it could be optical lithography tool, right, projection optical lithography tool uses extensive lens system, right? A lot of interesting optics goes in there, including telescope designs, right? We don't use electromagnetic designs anymore, right? So it's not yet. Some are using it, but it's not really common to use EM solvers for lens design. What we do is simple ray model. So all you need is a simple lens system, right? And then you have light source, or let's say you have the object, and then all you do is drawing straight lines, right? And then you will see how the image is formed, right? So you don't need complex mathematics here. This can be easily approximated to simple geometric axis. So you have a object plane, and then you have a image plane, and all you have is nothing but geometry here, rather straightforward. Okay, and this imaging using very simple lens systems, right? So this is called stigmatic imaging, right? Stigmatic imaging. And then in a perfect lens system, you will have, perfect reproduction of, whatever object that you have onto the image plane here, right? So there will be a perfect uh, 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 transfer of image from one object to the image plane here, right? I'll not talk too much about the imaging part because Ambarish has a separate section for imaging, but I'm putting this in the context of ray optics. So the stigmatic imaging is all perfect provided your lens is perfect, or what we call ideal lens, right? What I mean by this is the curvature is really perfect. You don't have any uh, defect in the material that you have here and so on, right? In a moment we will talk about the surface and so on. But in the presence of non-ideal lens, the image is not going to be perfect reconstruction of the object, right? And that is limited by what we call aberration limitation, right? So lens aberrations, right, or non-idealities in the lens system. So in order to understand even the simple lens system, one need to understand how the light propagates through this, right? So it comes through here, right, and then does some sort of refraction, and then it goes through, right? And what is happening here is something one need to understand. um, in a continuous or homogeneous medium, you don't have any issues, right? So it just follows the straight line. But then the moment it interacts with a medium, there is something interesting happening. The direction of light actually changes, right? So we need to understand that, and that is the whole idea of law of refraction. And you will also have reflection out. So there will be light that is reflecting out, right? And that is also governed by the change in the refractive index or the density between the medium. So this is what ray optics was able to explain really nicely, right? And that is the reason why even today we rely on ray optics for all lens and large optical design, right? So let's look at how to build this model, right? So the ray model starts by looking at the light source, right, as a point source, and it emits a ray from that point source. But we all know that, the size of the light source is not infinitely small. There is a finite size, right? So it has finite size. And then how do you approximate this? If you have a finite size, the best way, I mean, as mathematicians, we know is discretize the space, right? So you discretize the space, and if you have a surface that is emitting, you just discretize the surface to a small a surface, let's say ds, right? And that is emitting a reasonable solid angle of light, right? And that is what you see here. Your solid angle here is d omega, and ds is the smallest surface area that you have. And what is le? Some of you might have gone through the lecture. What is l? Did you look at l? Or instead of l, I would say f, right? So f is the
Radiant flux.
radiant flux. Yeah, so there is a radiance, right? So here l is
Radiance.
yeah, L is radiance here. So either F or L. F is the energetic quantity here. L is also representing here the flux that is coming out. All right. So if you put it all together, this is how much you are getting out, right? And this is a very simplistic way of looking at how light could be, imagined or viewed coming from a finite size source. Okay, because the moment you say the light has a finite size, you have this problem, right? So if I take a light source of certain area, so each point is going to radiate in its own way, right? So how are we going to understand this, right? So of course at the end you integrate all over it, right? But then you take the single array and then we'll try to understand what happens to this array. All right. There are few postulates of array optics, okay, um, that we should understand before understanding reflection and refraction. One is, we all now very much agree to this: light propagates as rays. Okay, so it originates from a source, and it can be detected, right? So it should be detected by a detector at far field, all right, at the reasonable distance wherever you want. Then only you say there is a ray, or there is light present. If the detector is not detecting any light, there is no definition of light and there is no definition of source either. So we should be able to detect it. And the next thing is the optical medium, right? The medium through which light is propagating is characterized by a quantity called refractive index, right? So this refractive index is nothing but, you know, a ratio of speed of light, right, in the medium to on and speed of light in vacuum, right? So this ratio, right, is something that we should all know, that determines the refractive index, or what you say, how dense the medium is, right? And we all know that it's always going to be greater than 1, because the maximum speed of light is in vacuum, but any medium is going to slow down light, right? So that is the reason why the refractive index of light in medium, in any solid medium, is going to be 1. Okay, so that's fundamental. So again, when we talk about medium, the medium could be homogeneous or inhomogeneous, right? So what I mean by homogeneous is, if you in the last class also we looked at it, right? So if you take a volume here, right, say z, x and y, right? So the density of this medium, right? So we talked about refractive index n, right? So n is the refractive index, and and if it's a one-dimensional quantity, it's a ray, right? And the ray would only feel the refractive index or the density along this direction, right? So we can call this as refractive index along z direction, right? So if it is a homogeneous medium, then what it actually implies is whichever direction you go, right, it's isotropic in nature. So that means nz equals ny equals nx, right? I can even go further and then say nab, right? So this a and b are, x, y and z, right? So nxx, nyy, whatever, if you want that. So this is all the interplane that you are talking about. All this are identical, right? So this is what we call homogeneous medium. So in a homogeneous medium, right, we need to define two things. One is geometric path length and optical path length, right? So geometric length we all know. So if you are going from point A to point B, you measure the distance between it, right? So AB dash, so that will be AB bar, that will be your distance between point A and point B. But light doesn't take that into account, right? Light actually feels the medium, right? So there is something called optical path length. Your geometric path length and optical path lengths are different. All right. So let us look at that why. Right? So I go from point A to point B, right? So your distance is this, right? And now this is geometric length, right? So now I bring in a medium theory here. So I'm putting this inside a medium and I'm giving a certain refractive index to this medium. So if n equals to 1, so the distance between A and B remains the same. If I put n equals 2, the distance between A and B still remains the same, because the size of this particular slab, right, of material doesn't change. But then the question here is, if I put light inside the system, so I'm going to put a wave of light here. So the light is focused into this part, and then we want to get the light out here. Okay, and then this is the distance it is going to travel. Okay, so for all geometric purpose, the distance between these 2 points is AB. But then the light, as we know, interacts with the medium, right? Because it interacts with the medium, it feels a different length. So when the refractive index is 1, it feels the medium is loose, let's say, right? It's very free for it to move. But then if you put a denser medium, if n equals 2, it feels like, there is a resistance to its flow, right? So because of that, optically it travels longer. So that how much longer depends on this n. So n times AB is the length that it travels in the medium. Okay, so this is what we call optical path length, OPL. If you put n equals 1, right, this is air. So optical path length and geometric path length are equal, right, when n equals to 1. So when n is not equal to 1, right, OPL and geometric path lengths are not equal, right? So your geometric path length is going to be smaller than, or let's say longer than the geometric path length. Okay, so light slows down, right? When light slows down, you feel that it is longer. All right, so this is the formulation for that. So the optical path length is nothing but, um, n as a function of r. Here r is the position component here, and ds is the distance that you travel, right? So between A to B, this is actually the optical path length. Is that clear? So this becomes much more interesting when you have anisotropic medium, right? I'll just give you a hint because I can't resist now. Um, so let's go back to this cube, right? So imagine here nx, ny, nz, all of these are identical now. So light can move in any direction, right? Uh, any direction it wants, right? At after a certain point of time, you will find the light at the same, contour, right? You can easily predict it. And now in a inhomogeneous medium, right? So if you have in a inhomogeneous medium, you will, this is not true, right? Right, so this is not true anymore, right? So this is the worst, I mean, let's get worst case scenario where all the three axes got its own refractive index, right? We saw earlier, there are crystals, birefringent crystals, right? That propagation in two, there are two possible refractive indices, right? If the light is propagating in x, it will travel at a different speed compared to y. So in this case, what is going to happen? It's an interesting view, right? So you won't be able to find the light at the same contour anymore. It's not going to be a circle anymore. Okay, when you allow it to propagate. Um, if I say nx is greater than ny, let's not worry about z at this point. It makes life a little easy to understand now. So in x direction, light will go much slower, right, compared to y, right? Because refractive index of X is higher than refractive index of Y, right? So the higher the refractive index, slower the light is going to be, right? Because C by N, right? So remember this. So because of that, now after a certain time that you spent in this particular crystal, X, it would have, propagated much shorter distance compared to Y. And at that point, what you will have is something like this. It's not anymore a circle, right? It will be some sort of an ellipse, okay? Starting from this, right? So this will give you an idea about what are all the interesting things you can do to light if you have an inhomogeneous medium, right? Sometimes this is very useful in manipulating light propagation. Sometimes it can be really pain in the neck to control light propagation through these kind of inhomogeneous mediums. Do we have some questions here? Okay, I
Yeah.
see question there. Yeah,
So,
yeah, please go ahead.
yeah, so actually there is any typical example where we have refractive index is less than 1?
Uh, see, less than one for naturally occurring material is not there. Okay, um, but you can make what you call photonic structures, right? This N is derived from the dielectric constant, right? The permittivity, right?
Yeah.
So what you can do is you can actually create artificial material, right? When I say artificial material, these are all sub wavelength scale or wavelength scale periodic structures. um, Through engineering the structure you can actually um, uh, uh, get what we call zero epsilon, right? So the dielectric constant is zero, all right, or what we call near zero, and sometimes even negative, all right. So there is negative refractive index concepts are also there, right? So we will briefly touch upon these concepts perhaps in wave optics or layer medium. As a naturally occurring compound material, getting it less than 1, n less than 1 is not possible. However, one can engineer structure, right, with photonic crystals, they are called, or metamaterials, right? Photonic crystals, metamaterials is a large vast area that deals with controlling and manipulating light with wavelength scale structures, all right.
Yeah.
Does that answer the question?
Yeah. Thank you.
The straight answer is yes, but then it needs a little bit of jugglery. Is this concept clear? Optical path length and geometric path length. These are two different uh, quantities. You should clearly understand this. Okay, because more often when you are doing optical design, you forget that optical path length is what matters, not the geometric length. All right. So one of the important implication of ray theory, or understanding this optical path length, is the propagation length and also direction. All right.
Sir,
So this is all from
sir,
Ferbet.
this
Yeah.
is Anupama. There are
Yeah.
two more questions,
Yeah.
and I saw
Yeah.
someone
Please.
who has raised their hands. Javed.
Please go ahead. Please go ahead.
Hello, sir. Sir,
Yeah.
I wanted to know the in materials with n greater than 1, we see that
Uh-huh.
there is some interaction between the light and the medium, but there is no change in energy of the light. So what is this kind of interaction? Can you please explain?
It depends on the
Okay.
frequency.
So yeah, somebody already mentioned. So this when we say interaction, right? It's one thing that all should understand is you know the big difference between physicists know this, the fermion and boson difference, right? For those of you who are still wondering about what this difference is, I'll make it very simple. Okay, so we can compare electrons and photons. Okay, so electrons, they readily transfer energy. Okay, they are good in doing that, and that is the reason we were able to build the circuits and all kind of interesting things with electrons, right? Photons will not share energy. Photon, very hard to get energy out of a photon, right? The reason for that is much more complex. I don't want to digress here. So this energy transfer with from a photon to any other photon or to a material is not straightforward, unlike electrons. All right. So that is one of the reason why it is hard to use photon for a lot of application, particularly where you do interesting computation and so on. Having said that, light is propagating through a medium, right? You see, light is interacting with the material, right? So what are all the kind of interaction the light can have with the material? So that is the question here. And why the property of material is not changing, and vice versa, why the material property is also not getting changed, because there is an interaction. We say there is a light matter interaction here. There are two ways to look at it. One is a passive interaction and one is an active interaction. So the way to look at this is you are the propagation, whether it is elastic or inelastic. All right, interaction between two bodies. All right. So in one, you will transfer energy and you will generate new energies going forward. In the other, you will not. Right, you will only lose energy. All right. So the whole collision, right, also requires some sort of mediation, right? So if you have done vector calculus, you know that you need to have the phase matching in order to transfer the energy. In this case, the frequencies are so high that you are not going to interact with the atoms, right? So that there is an energy transfer that is happening at the lower power levels, at least. Okay, so this interaction that we talk about while propagation is merely a passive interaction. It's almost like a water going through what you call a bunch of pebbles that is arranged, right? So in the river you have pebbles which are there arranged in certain fashion, let's say, but water flows through this, right? And you will see at certain flow rate, the water will not get disturbed by the presence of these pebbles, right? So pebbles got its own size and so on, right? So you consider those pebbles as the atoms that are sitting inside the medium. So this is a very passive interaction. So nothing is done to the light. But then you increase the speed of the flow. So at certain speed, beyond a certain speed, you see ripples forming, right? So the whole laminar flow is now disturbed and you will have turbulent flow. And this turbulent is a direct, what you call the phase, if you want a phase matching or energy transfer, or there is a coupling happening between the pebble as an object and your water that is flowing through. You can use the same analogy here as well. So when you are flowing through this material matrix at certain powers, you have very weak coupling between light and the material. So literally nothing happens. That is what we call passive interaction. So when the power of light increases, right, so the interaction becomes stronger and stronger, and the material will induce some change to the energy flow. And if I even increase it much more, right, the light flow will affect the material itself. You can also observe this in the water flow example. So the pebbles are there. If I increase the flow rate even higher, then the energy that the water has can actually dislocate the position of the pebbles there, provided you have enough energy. So what this actually doing is creating, material deformation, right, to a large extent. All right. So the coupling becomes stronger and stronger. The same thing happens in the light matter interaction as well. When you increase the power beyond a certain power, you will start changing the material property. Okay. So these things, we'll look at it a little bit more carefully, because what I'm saying now is all qualitative, right? So that you can link these phenomena. But then we need to mathematically show this, right? And that is what we will do in once we done the wave theory. We have light matter interaction, right? So how do you build the material model, and actually how this refractive index is defined, right? So when we go there, we will clearly see what is the implication of light and light frequency on the refractive index. Okay, but for the moment, I think this analogy one can use to understand the flow, right, without having an effect or having no effect. Okay, so bear with me. I hope this understanding kind of gives you a way to visualize.
Yes, sir.
All right. You said there are two more questions. Is that all clear? Is there one more question, or it's all?
There are more questions in the chat.
Yeah. Why don't you just
Yeah.
tell me those?
Can you explain more about phase?
Okay. Just bear with me. We are in ray optics. Here we don't really understand phase. Okay, that's given. Let's not worry about it. In wave optics, in the next section, I will talk about the phase, and there are some illustrations that will help you. Let's move on. What is the next question?
What is the meaning of paraxial optics?
Somebody has read a little bit more. So in geometric optics, right? Let me see if yeah, right. So here I've used a very simple lens system to to show that the object is here and image is here, using this, right? So paraxial optics or paraxial treatment is basically looking at a very small angle of light matter, or light and object interaction. For example, paraxial approximation is primarily looking at a very small angle from the central axis, right? So if you draw a straight line, right, so that is the optical axis, let's say, right? So the paraxial approximation is small angle around the axis here, right? And also this is true when your lens is very thin. For thin lenses, you don't need a large angle approximation. So all this thin and very small angle approximations, so very close to the parallel light propagation here, right? So that is the paraxial approximation. So these things, I think Ambarish will talk about when he talks about lens systems and imaging. All right. So in imaging, this is a very important topic, paraxial approximation. Okay. Other questions?
Yeah. If n is less than 1, then light should travel in a medium at a speed higher than that in vacuum. Is it possible?
It is not possible. So that is not possible, right? Because you will be violating Einstein, right? So it won't be less than 1 for n, right? But you could there is a discontinuity there. Okay. That is an interesting physics from metamaterial side, not from the bulk material, where you avoid the zero. So zero will be discontinuous. Okay. So there is no solution to the dielectric constant of this particular metamaterial at zero, but near zero is what we talk about, right? So near epsilon zero, right? So that's that's how you formulate it, right? Negative, it's basically in the direction, right? Not necessarily in the propagation. So yeah, zero is not really zero. We'll be violating physics there. There are other parts where you will feel that we are violating physics, but we won't be. But in this sense, getting absolute n less than 1 is not happening. Yeah, any other questions?
Okay. Yeah, we are talking about circular paths in 3D object. Are we deviating from straight light property of light?
No, the ray is one dimensional, right? It has a point A and point B, but I can hold this ray in any direction I want, right? Because the world that we live in is three dimensional, right? If you want, you can do four dimensional as well, if based on how you define it. But from geometric perspective, right? It is just three dimensional. So the ray can travel in any direction, right? But still, it's a one dimensional definition, right? We are not putting relation here, so that is why I mentioned, right? There are two rays, one is going in this direction and one is going in this direction, right? So this is how ray is being assumed, right? There is no relation between these two except the fact that they all originate from one point. Apart from that, there is no relation, right, while they are moving. So we are still within the boundary of the ray definition and the postulates of ray optics, but we can use the propagation in three-dimensional and in real space to understand the implication of homogeneity and inhomogeneity here. If you bring in the relation between the two rays, then I think we have some issue there. Okay, but here we are not. Apart from the fact that they originate from the same source. Anything else?
That's
Sir,
also.
sir, sir,
Yeah.
sir.
Yeah. Please go ahead.
Earlier scientists were talking about ether. So does it to do something with the refractive index that we are talking now?
Yeah, the ether definition of ether was a little different. Okay, it was not just a medium, right? The postulate there was light cannot travel in vacuum, it needs a medium, and this medium in air, right, was called as ether. So that was the what you call the wrong thing about the whole ether definition, right? So they said light can only propagate in a medium, it cannot propagate in vacuum. And since air is there, right, so air was not considered as a medium, they said we call this as ether. So you need ether for light to propagate. Without ether, light wouldn't do that. So that was the problem with the ether. Okay, it was, if it was
Ether
like
had
medium theory, then we would have understood it. And if they followed up with a statement saying that you don't need a medium, but if there is a medium, we call this as a ether. But no, they started off saying that light cannot travel without ether. So that's a problem.
Sir, it had to do nothing with density of material.
Correct. They did not say anything about it. That was the problem with the ether. Okay. All right. Moving on. Fermat. So we briefly mentioned about Fermat during our introduction, right? So Fermat actually formulated or just proposed that light will take the shortest path or shortest time, right? And that is what you see here. So this is the mathematical formulation for that. So going from point A to B, light will follow an extremum. Okay, so extremum, they said it is extremum. Nobody said, or even Fermat did not say that it is minimum or maximum, right? So it could be maximum length or it could be minimum length, right? So that's the extremum means, right? um, Going from point A to point B. More often what we see is, in some cases you will see light takes the longest path. We'll see that in our guided wave system, where it is possible for light to take the longest path, um, to not to violate laws of physics. But then in classical sense, in most of the time, light always takes the shortest path. Okay, so this is how it was formulated. Okay. um, and one can actually use this for understanding, but this is just a principle, right? So we cannot use this to derive any law out of this. Okay, because this is not a fundamental law. This is just a principle that was proposed, but it stays as a principle, and no laws were derived from this, unlike the refraction laws from early on. All right, is that clear? That's the Fermat so far. So these are all the postulates of ray optics. Somebody,
Hello.
I heard some
Yeah,
rumble.
sir.
Yeah.
Yeah, sir. Fermat's will say that the light path will be extremum, right? But how light
Correct.
understand that this is the maximum or minimum? Like, that is a confusion I have.
Interesting question. I used to ask that question to. I'm getting an echo. Uh, so I used to ask this question during some of my popular lectures. So light is not an intelligent being, but it understands that I should take shortest path. All right, there is an underlying physics governing this shortest path. All right. Um, with ray optics, it becomes very hard to understand. We can take a stab, but I don't want to do it now. But this concept of light being intelligent, we will discuss this in wave optics, particularly in guided wave optics. Okay, so light is very intelligent. It knows what is ahead, and it can take corrective measures not to violate physics. Okay, so that is the beauty of light. So I'll definitely talk about this, because it's one of my favorite topics, that light is intelligent, right? Though we use that as a simple form of energy, it does, and it naturally happens. And in order to understand that, we need to understand the wave optics, and on top of it, we need to understand the electromagnetic nature of it, and how it interacts with the medium, right? So that medium interaction of a wave is very essential to understand why light is intelligent. All right, so it is not dumb, it is intelligent. And there are coupling in physics that makes this intelligence um, work out. All right, so just hang on till we do the guided wave optics. There I will explain you this. All right. Moving on to the reflection. Oh, we are spending a lot of time in this array already. So reflection is a very simple phenomena, right? So the way that the reflection theory was formulated is, you have an incident wave here, incident ray, and there is a reflected ray of a shiny surface. So it has to be a mirror. Okay, the surface is reflecting. Okay, and both incident ray and the reflected ray, they should be on the same plane, or they will be on the same plane. Okay, so what do we mean by same plane? So you have you have, this is the surface, and light comes in and goes out, and this is the incident angle and the reflected angle. Oh, sorry. Okay. um, so this plane, right, what we are talking about, so this is xy plane. Okay, so both the incident ray and the reflected ray will lie in this xy plane. Okay, so it will not change the direction or direction of reflection. All right, So this might be little weird, right, for you. Purposefully, we use curved surfaces to explain this. If it is a flat surface, it is obvious, all right? But this is also true in a curved surface. The reason for this is a ray, right? Ray is defined as infinitely small, dimension, right, quantity here, right? So the ds is infinitesimally small. So when it interacts with a curved surface, right, the ds, right, that you have here, the surface of interaction that here is much smaller than the surface, the curvature that you have. For all practical purpose, this surface can be treated as flat. Okay, there is piecewise flat here. All right, so that is the reason why we don't have to do much about curved surfaces. Whatever reflection theory we use, that actually works out for curved surfaces as well. All right, so the incident and reflected angle should be identical, right? And there are various ways that we exploit this reflection theory. One is a simple mirror, right? So you have incident rays coming in, and then you will have reflected ray. All right, so you can see here, you will only have divergence of rays from a flat surface. So any flat surface, you will only see diverging rays, right? It is impossible to concentrate or focus light with a flat surface, right? This is all governed by simple geometry. That's what we see here. And when you draw this imaginary lines, right, on the other side, so P is there and you have P dash. So these are all imaginary lines from the reflected ray. If you draw that, you will see those rays, right, congregate at point P dash. So P dash is actually the image of P. It is not real, right? So this is how you get an image out of a mirror or a shiny surface, right? This is because of this particular phenomenon. Yeah.
Sir, this is Karthik. I have a question. So
Yeah. Please go ahead.
you said that rays reflect from curved surface to means incident angle and reflected angle is same for curved surface because light rays are infinitely small. That's what you said.
Correct.
But
Correct.
sir, I mean they also have wavelength. So for visual rays, wavelength is like 0.6 micrometer etc. Means if we take large wavelength, then will they reflect to the curved surface because then the irregularities in the curved surface or the curve will become similar to their wavelength. Will they reflect properly then?
Yeah. Okay. So before I answer that question, I think most of you must have understood this question, right? The question is, what happens to the wavelength and so on. Can anyone respond to this answer question? What you guys think is happening here? Why this curved surface doesn't really matter?
Uh,
Yeah.
okay, so this is like ray optics, and the first postulate of ray optics was that the wavelength of light should be like negligible compared to the dimension of the material that it is interacting with, right? Uh, like wavelength is very small with respect to the say anything aperture, curvature, anything, so that it actually sees them as like straight, like flat surfaces.
Yeah. So that's basically the answer, right? In ray optics, there is no uh, let's say we assume that there is no wavelength present in here, right? That is how we draw this ray. Ray is the direction of propagation of light, but we don't talk about the wavelength of light here. Okay, so the wavelength of light is very let's say small compared to the object that we are talking about. All right. So that is one of the postulates or assumptions, if we can say, in a civilized form, we call it as postulates. But that is one of the important, postulates or assumptions that we make. All right. So wavelength is taken out of the whole discussion here. Right. That's an important question that you asked, so that everyone also gets a clarity on this. We take the wavelength out of this. All right. So all along the discussion, we did not say anything about the wavelength. We only talked about ray, right? Is propagating. So we all approximate that. Okay. So that is the reason why, the size of the object, right, or the curvature doesn't really matter here, because it's infinitely small. Got that?
Yes, I got it. But I mean, if we do reflection of big wavelengths, then there would be change. So will
Absolutely.
there?
Your understanding is correct. Okay. So light in conventional, or in a better discussion, apart from ray, you should also look at the wavelength, okay, of light, and also the object as well. Okay. So the size of the object and the wavelength does play a role here, right? In this case, we are not looking at it, and that is the reason for not taking into account, right? um, so just I want to give you a simple thumb rule here, right? Normally, for this ray optics, or the size of objects that we discuss, right? uh, we consider, the objects are larger than lambda square. Okay. So that is how we handle these things, right? So lambda square, both the surface, right? So if the surface that you're interacting with is larger than lambda square, I think you can easily or with confidence use the ray, okay, model and ray approximation. Lambda square is basically, the area, right, that a wave can fill up. Good. So that's on that. Let's move